You just click play. Your character loads in. The frame counter in the corner says 144. You feel like your CPU is working as hard as it possibly can. Right now, this very second, just to keep that number steady. But the real answer is far stranger. Most of the time, your CPU is doing almost nothing at all. It is sitting there, waiting. For milliseconds at a time, thousands of times a second, one of the most powerful chips you own is just idle. Why would that be true? And if it's true, what is it actually waiting for? Let's start with what you think is happening. You imagine your CPU as a tireless worker, crunching numbers nonstop, racing to keep up with your GPU, your monitor, and your mouse movements. That picture feels right. It feels like effort should look like constant motion. But modern CPUs run at speeds that are almost impossible to picture. A processor clocked at 5 gigahertz completes 5 billion cycles every single second. In the time it takes you to blink, your CPU has already finished more calculations than you could count in a lifetime. So here's the uncomfortable truth. Your CPU isn't struggling to keep up with your game. Your game is struggling to keep up with your CPU. Think about what actually happens when you're playing something like a competitive shooter. Your CPU calculates player positions, physics, hit detection, and game logic. Then it hands a finished set of instructions to your GPU, which paints the actual picture on your screen. But your GPU takes time to do that. Rendering a complex frame with lighting, shadows, and particle effects can take several milliseconds. And during that time, your CPU has already finished its job. It's sitting there, waiting for the GPU to catch up so it can send the next batch of instructions. This is called a synchronization gap, and it's one of the most misunderstood parts of gaming performance. Digital Foundry has spent years breaking down exactly this kind of frame pipeline in their technical deep dives, showing how CPU and GPU workloads rarely finish at the same moment. There's almost always a gap, and that gap is where your CPU just waits.
Now, here's where it gets stranger. You'd think a chip sitting idle would just power down and rest, but that's not really what happens either. Modern CPUs use something called clock gating and power states, technologies pioneered and refined by companies like Intel and AMD to manage exactly this kind of downtime. When a core has nothing to do, it can drop into a low power state for a fraction of a millisecond, then instantly snap back to full power the moment new instructions arrive. Your CPU isn't lazy during these gaps. It's efficient. It's constantly toggling between full effort and near total rest, sometimes hundreds of times per second, and you never feel a single transition. But why does this matter to you, the person actually playing the game? Because this waiting is the hidden reason behind something you've absolutely experienced: frame time inconsistency. You know the feeling. Your frame rate counter says 144, but the game still feels like it stutters for a split second. That's not your imagination. That's a moment where your CPU finished its work early, then had to wait a little too long for the GPU, or vice versa, creating a tiny hiccup in the rhythm between the two. Your eyes don't see frame rate. Your eyes see frame time, the gap between each image. And when those gaps become uneven, that's when smoothness disappears, even if the average number on screen looks perfectly fine. Here's the twist that changes everything. You'd assume a faster CPU always means a smoother experience, and that's often true, but it's not the full story. If your GPU is the one taking longer to finish each frame, then upgrading your CPU won't fix anything. Your CPU will just wait a little longer instead. This is what's known as a GPU-bound scenario, and it's the opposite of what most gamers assume when their PC feels sluggish. Gamers Nexus has demonstrated this exact scenario repeatedly in their benchmark breakdowns, pairing high-end CPUs with lower-end GPUs, and showing frame rates barely move, because the bottleneck was never the processor waiting to think, it was the graphics card waiting to draw.
So which one is actually holding you back? That depends entirely on the game. Open-world titles with sprawling AI systems, physics simulations, and complex logic tend to lean heavily on the CPU. Games with dense visual effects, ray tracing, and high-resolution textures lean heavily on the GPU. And in both cases, the component doing less relative work spends more time waiting by. Microsoft's own DirectX documentation describes this handoff process in detail, outlining how command buffers are queued from CPU to GPU and how mismatched pacing between the two creates exactly the kind of stutter you felt, but never had a name for. Now picture your CPU's waiting behavior mapped out as a heartbeat. Work. Wait. Work. Wait. Thousands of times per second. Most of those waiting periods last only a fraction of a millisecond. Invisible to you. Harmless. Even helpful for keeping your system cool and efficient. But every so often, a wait stretches just a little too long. A background process interrupts. A driver takes an extra moment to respond.
Windows itself briefly steals a CPU cycle to handle something unrelated to your game entirely, and that one slightly longer wait, that's the stutter you feel in your fingertips a half second before your brain even registers it happened. This is also why upgrading your CPU sometimes produces almost no visible improvement, while in other games it transforms your experience completely. If a title is CPU bound, meaning your processor's calculations are the true bottleneck holding back your frame rate, a faster chip reduces those waiting gaps directly, and you feel it instantly. If a title is GPU bound, your CPU is already comfortably waiting most of the time, twiddling its digital thumbs, and no upgrade to it will change what's fundamentally a graphics card limitation. Have you ever wondered why some competitive players insist on absurdly high frame rate targets, sometimes 240 or even 360 frames per second, on monitors that can barely display half of that? It's not really about the number. It's about shrinking those waiting gaps as tightly as possible, minimizing the moments where timing becomes inconsistent, chasing an almost impossibly smooth rhythm between processor and display. NVIDIA's research into low-latency rendering technologies exists almost entirely to address this exact problem, reducing the queue depth between CPU-ready frames and GPU-rendered output so that waiting time translates into less input lag, not just a bigger number on a benchmark chart. So the next time you load into a match and your CPU usage monitor shows something like 40 or 50%, don't assume your processor is holding something back. That number isn't weakness. It's discipline. Your CPU has already sprinted ahead, finished its calculations, and is now patiently pausing, ready to respond the instant its partner catches up. It's not lagging behind your game. It's leading, then waiting for everyone else to arrive.